In the name of Allah, the Compassionate and the Merciful. Hello guys, my name is Salar Delavar Qashqai, and in this video we are going to talk about the ductility damage index based seismic performance assignment of this railroad bridge. You see that guys, in here this railroad bridge have three span with different length, and this section of this Warren railroad bridge has this, and railroad at the top of this truss, and then we're going to model it with Opensees with just one side, not 3D model. We're going to model as a two-dimensional modeling and use two different sections for this modeling. So for elements of top and bottom of these sections, we use one box section, and for diagonal elements also we use different box section. So for modeling of this Warren railroad bridge, we use two different box section. So you see that guys, for modeling of this old railroad bridge, many sections is going to be used with bolted sections, yielded sections, So we're going to model it with two different box sections with different width and thickness. So in the first analysis, we're going to have an ductility damage index response spectrum, and in the second analysis we're going to have an sensitivity analysis with the changing of the box width and thickness from minimum to maximum, and then seeing the response spectrum and also damage index for different thickness and width of these elements variety. And in the third analysis we are going to have a movable displacement, so we are going to change the displacement from this point until this point, and then this point to this point, and also changing movable displacement from this to this, and then running the pushover analysis at the vertical direction and seeing the result. So for evaluating the response spectrum of this Warren railroad truss, we're going to run two kind of analysis. First of all, nonlinear static analysis, which is called pushover analysis, and the second analysis is nonlinear dynamic analysis in a vertical direction. So we're going to apply the vertical seismic response, and then running the nonlinear dynamic analysis and also pushover analysis. So let's see. So if we run the pushover analysis, we're going to use this formula to calculating the structural ductility damage index. Delta D comes from ultimate maximum displacement during the nonlinear dynamic analysis at the defined node, and then yield and ultimate displacements comes from pushover analysis. And then with this formula we're going to calculate the total structural ductility damage index. And you see that, guys, for calculating this delta D, we are going to run the nonlinear dynamic analysis and then finding the maximum absolute value. And you see that, guys, based on this process we can find the elastic stiffness, plastic stiffness, tangent stiffness, and also ductility damage index, overstrain factors, yield displacement, ultimate displacement, demand displacement, also the structural ductility damage index. So let's back to the response spectrum file. So in our analysis we're going to calculate the actual ductility damage index for just 6 elements, structural ductility damage index for total of damage of these structures, and also actual strain damage index. So this formula comes from demand strain, yield strain, and ultimate strain. So this two process comes from very simple formula for truss. For example, FAU equals to area of each element truss multiply yield or ultimate stress of these structural properties. So for example, in here of the FAU equals to area multiply ultimate stress. So in the process of analyzing we're going to output these elements properties for strain, stress, and axial forces, and so on, and then running the incremental displacement at the node 47 and 16, and also outputting these elements strain, stress, and axial force. You see that, guys? And also this element and this element, strain, stress, and axial forces. So this bridge has 3 span, and then we're going to run just one side of these structures as a 2-dimensional modeling. If we run the analysis with 60 increment, you see that, guys? Displacement response spectrum, velocity response spectrum, acceleration response spectrum, between value near 0 and 36.36 seconds. It's going to be calculated with 6 iterations, actually 6 increments. And also if we are going to plot this response spectrum with natural frequency, it's going to be shown in here as a logarithm base. You see that, guys? And let's see, and you see at the each analysis we're going to output displacement time history, velocity and acceleration, and also base shear time history. And this graph, as I'm going to show you, is the last analysis of this response spectrum. And let's see other data. You see that, guys, in here we have (121 elements and 62 nodes and 4 simply support connection as a real model. You see that, guys, in here we have 1, 2, 3 and 4 simply support connections. And let's see other data analysis. So if we run in all data for this 60 increments, you see that, guys, structural ductility damage index response spectrum is going to be shown in here. So at the first, damage index comes from low, and then it's going to be up. And you see that, guys, with this period it's going to be little smooth. And let's see the other parameters data, such as axial ductility damage index. So in here we are going to has a yield strain, demand strain, yield strain, and ultimate strain of this 6 element. Element number 6, 16, 26, 50, 90 and 110. And you see that, guys, element axial strain is going to be shown in here for these 6 elements, and also axial force is going to be shown in here based on pushover analysis and then dynamic analysis. So we're going to run 2 kind of analysis. So we have 2 kind of data, such as pushover analysis and then nonlinear dynamic analysis. And you see that, guys, elements stress and also axial strain damage index, you see, based off this formula, you see that all the values is in negative. So it shows that the these structures between this period until this period, it has unsafe damage index. So in here we are going to say that we are in this graph has safety damage index. Okay, so let's see the other values, outputted data. You see that, guys, in here we're going to show the difference between dynamic and pushover analysis of displacement, and also base shear and displacement ratios for seeing the result. You see that, guys, it has this shape, and then it shows that if we use this polynomial regression, you see that, guys, it has very good fitted data with good R square, and you can predict the next values if we increase the mass or even increase the displacements. So you can predict with the very good coefficients values. and let's see the other outputted data. Yes, you see that, guys, in here. Result between acceleration and displacement response spectrum with using this polynomial regression. It has very good fitted R squared, and also relations between acceleration, displacement, and velocity response spectrum with the 3D plotting. It has this shape. You see that, guys, in here. And also let's see results between actual ductility damage index of elements number 6 and structural ductility damage index. It has this shape, and we use polynomial regression. You see that, guys, it has very good R squared, and you see that with in x-axis we use this formula for element 6, and for y-axis we use this formula, and then based on 60 analysis we're going to output the data, and then using to graph it and find the best curve fitted line. So let's see the other outputted data. Let's see. Yes, you see that, guys, in here. Structural ductility damage index response spectrum and displacement response spectrum. It has this shape. So with using polynomial regression, you see that, guys, R squared is very good for curve fitting data, and also relations between velocity response spectrum and structural ductility damage index. It has this shape. You see that, guys. So it shows very good fitted with R squared this value, and also relations between structural ductility damage index and accelerations. So it has this shape. So with using polynomial regression, R squared equals to this value. Not good, not bad, but for this very complex structural modeling, 75% is very good in my opinion. And also let's see the other parameters modeling and outputting data. Yes, in here we're going to model the actual ductility damage index and displacement response spectrum. It shows very good linear relations between these two parameters. So, and let's see the other outputted data you see in here. Relations between actual ductility damage index of element 6 and velocity. It has this shape, and with using polynomial regression, R squared is very good. And also relations between actual ductility damage index and acceleration. It has this shape, so it shows that very good R squared. And relations between displacement and ductility damage index response spectrum and actual ductility damage index spectrum for element 6. It has this shape. You see that, guys, in here. We're going to plot it, and then last pushover analysis data. It has this shape. and then you see that, guys, structural ductility damage index is going to be calculated. So in here we have softening, because mass at in this step we have very high mass of this at the each node of these structures, and then we're going to run the pushover analysis. So if we back to the response spectrum analysis, we're going to add the mass at each point of this structural node as a two-dimensional modeling, and running the nonlinear dynamic analysis with the vertical accelerations and vertical incremental displacement. So at each node of these elements we have constant mass of these values at each node. So, and let's see the other outputted analysis data. And let's, in here I forgot to show you the correlations, relations between each value. You see that, guys, correlations between most of the data, it has very high. So you must omit some data to finding the best optimum curve-fitted relations, linear relations with the multiply regression. And you see that, guys, in here. In here, p-value in this and this is very high, so you can change it or omit it to find the best curve-fitted linear relations between each parameters. So in the second analysis of this Warren railroad truss, we're going to have a sensitivity analysis. So we're going to change the box section width and thickness of this element truss, which truss element truss at the bottom and top of this element truss. So not a diagonal element section truss, and then running the sensitivity analysis and changing the values, for example, for box width minimum to maximum, and also thickness from this minimum to maximum with 50 iterations, and seeing the result. So if we run this analysis based on pushover and dynamic analysis, we're going to output the elements strain, stress, and axial forces, and then seeing the result of this ductility damage index and also strain damage index. If we run it, you see that, guys, the response spectrum, the values change from this to this for period, and also displacement is changed, and also velocity and accelerations shape is changed. So the total of the structures goes to have a nonlinear behavior as a material and geometry properties, and also you see that this response spectrum with the natural frequency, it has this shape. And let's see, you see that, guys, all the forces is the same based on this analysis. And you see, yes, in here if we change the section box width and the thickness with the period, so the period it's going to be very low, and if we increase the box section width and thickness, you see that, guys, it has this shape. So in suddenly it goes very, very high for total ductility damage index. And then in here for axial ductility damage index, you see that, guys, if we increase the box thickness and width of this element, so the axial, it's going to be low. You see that, guys, it's going to be low. And then for element 70, it has this shape. And also for axial strain ductility damage index, we have this shape if we increase the section box width and thickness. You see that, guys, in here. And also for element 70, it has this shape. And you see that, guys, in here. Relations between axial ductility damage index for element 6 and structural ductility damage index, it has this shape with a very good R squared. You see that, guys, in here. And also relations between structural ductility damage index and period, it has this shape. So if we increase the mass in some point, like in here, structural damage index, it's going to be very goes up, and it shows that this value is very sensitive. So if you want to have to be safe mode, you must design the structures in these positions. Okay, guys. And if you the period of the structures increase from this point value, so the total of the structures are going to be damaged at all. And let's see, the other outputted data. Yes, guys, in here relations between displacement response spectrum and acceleration, it has very good R squared. And let's see the other outputted data for this railroad truss. You see structural ductility damage index response spectrum and displacement, it has this shape. So in here we suddenly going to have a damage of this total of these structures. So it is very sensitive. And also relations between structural ductility damage index and velocity, it has this U shape with not good R squared. And also the acceleration and structural ductility damage index, it has U shape with not good R squared. And also in here we're going to plot the element axial strain of this each 6 truss elements. You see that during the analysis, and you see that, guys, in here actual ductility damage index for each these 6 elements with this formula. So in this formula, yield strain and ultimate strains comes from the material properties such as steel yield and ultimate stress of this plate, and also demand strain comes from running the nonlinear dynamic analysis, then outputting the defined node at the corner of the box sections for outputting the strain and stress. So in our analysis, for calculating the demand strain, we are going to output this coordinate for outputting the stress and strain of each element's strain and stress. So let's see in here other outputted data to be shown in here. You see that in here element actual stress for different periods, it's going to be shown in here, and also element actual force based on nonlinear dynamic analysis, it's going to be shown in here, and also actual strain damage index is going to be shown in here. So in here FAD is a demand strain during the nonlinear dynamic analysis, and then in here we're going to calculate the actual ductility damage index, actual strain damage index. And let's see the other outputted data. Okay, guys, you've seen here relations between actual ductility damage index and displacement. It has linear, very good relations, and also actual ductility damage index and velocity, it has these shape relations with the good R squared, and also relations between actual ductility damage index and acceleration, it has this shape, so it has very good curve fitted data. And also let's see in here we're going to plot the structural ductility damage index and actual ductility damage index of element 6 and displacements. You see that, guys, it has this shape, so suddenly the structures is going to be collapse. So you must choose the best mass and then best seismic acceleration for running this process of these complex structures to finding the optimum solutions for retrofitting or fixing some elements properties. And let's see other outputted data. Yes, in here I'm going to show you that the relations between box with thickness and structural period, displacement response spectrum, velocity, acceleration, base shear, and different ductility damage index and strain damage index correlations. You see that, guys, in here. So in some parameters it's near to 1, so we're going to omit some parameters such as accelerations, or even this value as a actual ductility damage index of element 6 for finding the optimum linear relations between these all parameters with multiply regression. And also you see that, guys, if we run it multiply regression with all outputted data, some parameters such as this value, it has not good p-value, so we must omit it or change the parameters to find the good fitted relations between all parameters as a linear relations. And as a third analysis, we're going to have an movable displacement. So in here we're going to add a incremental displacement of each node. For example, this node, and you see that, guys, this node until this node, and then this node until this node. So we're going to run the nonlinear static analysis, which is called pushover analysis, for all nodes of these structures, and then outputting the result. So in this analysis, we want to find the critical conditions of imperfections which must be happening to the these structures when the railroads going to be damaged, or for example, imperfections happens during the structural life history. So if we run it as a two-dimensional modeling with the same properties which I told you, you see that, guys, in here. So we're going to change the node and run the pushover analysis. You see that, guys? So base shear, for example, base shear for these properties, so it has this shape. So for example, if we run the pushover analysis from this point to this point, so base shear relations, it has this shape. And also, let's see, if we run the pushover analysis from here to here, and then seeing the effect on base shear of node 2, so it has this shape. So in the total of the structure, this node calls let's see, 11, 21 and 31. So, and also let's see the other outputted data, relations between bridge bottom node and displacement. If we have a incremental movable displacement, it has this shape. So in here we have a very critical conditions, and then the structural displacements go down. Then in here we have a very smooth line, and then it's going to be 0. And also you see that, guys, if we increase the displacement pushover analysis in here, for example, at the bottom or top of increasing the displacement, you see that, guys, it has this shape. So we are going to increase the displacement in this node, and then seeing the effect on different nodes. So you see that, guys, in here we have in node 47 as an orange line. So it has this shape. So it has very critical conditions in these positions with the displacement, ultimate displacement of 50. And let's see the other outputted data for this movable displacement. You see that moving displacement and for element axial strain of different elements. You see that, guys, in here. For example, in here, element 90 has a critical conditions, and also element 50 and element 110. So these three elements has a diagonal elements of this Warren railroad truss. So it shows that the diagonal elements for this Warren truss has a very critical conditions as a strain and also a stress. You see that, guys? It is same as strain relations. And also, let's see the other outputted data. Movable displacement and structural overstrain factors. It has this shape. You see that, guys, in here? In here and in here, we have a very critical conditions, and we must take care of this overstrain factors. And also it shows that in here also, same as overstrain factors, we have a critical conditions, and also plastic and elastic flexural rigidity. It has this shape, and also yield displacement. You see that, guys, in here and in here at the middle side of each span of truss, we have a very critical conditions with the movable displacement. And let's see the yield based shear of structures. So it shows that the total base shear of this Warren railroad truss, it has this shape, and in here we have a critical conditions, and also ultimate displacement in here and in here. We have critical conditions with the movable displacement and also ultimate base shear, and it shows the same as yield base shear, same as this. And let's see, in here we're going to plot the base shear and displacement of incremental displacement with the movable displacement, and seeing the last data as base shear and displacement analysis. So it is very efficient. You see that, guys? If we want to model the truss as a railroad truss or other roaded truss, we must use this kind of analysis to find the critical conditions of the loading and the imperfections, to seeing this bridge safety during the any conditions which is going to be happen to this structure. So you must indicate the uncertainty conditions of the damage of this structure. So in this analysis we see the effect of different conditions which might be happen to these structures during the analysis. In here we're going to see some slide of this real bridge, this historical Warren Dick Truss Railroad Bridge over Colorado River in Arizona, and needless in California. Shows the details. So let's see some slide of these structures. I also added the link of this website and also paper which I used to outputting some data of this structures. So in here we are going to see the Opensees file and seeing the some functions which are used for running this complex Warren railroad truss. You see that, guys, in here. In here I added some links. You can follow it to see the real structure, properties, and shape of this Warren railroad truss. In here I defined many functions to outputting and seeing the result. And in here I used these formulas for plotting the polynomial regressions. You can change it with your own. And let's see, in here I used push or analyze functions for this cable truss. I import nodes and elements properties and width and thickness of each element properties, and also yield and ultimate strain of these properties, weight, and different nodes for having an incremental displacement, and also defining the ultimate displacement and adding the I for each iterations outputting data. You see in here I defined two different box section for diagonal and straight truss elements properties, and outputting the displacement and base shear for each nodes. You see in here, and running the analysis, and also dynamic analysis function with same properties, nodes, elements properties, and so on, and also mass and weight of these structural properties, and applying this ND01 for having applying the seismic accelerations in a vertical direction. It has this shape, and also I use the truss section for defining the element, and also in here we're going to output the element force, strain, and stress for define the node, which I defined it at the top corner of each box element, and then outputting the displacement, velocity, acceleration, and also base shear during the nonlinear dynamic analysis. And let's see, in here we're going to define the element properties for each span. For example, these properties for span 1, span 2, and span 3. So the height of this Warren railroad truss, and defining the nodes. So we have 62 nodes and 121 elements, and in here we're going to define each element properties. So in here we're going to plot the truss, and in here we're going to define the section properties for calculating a yield strain and stress for these truss elements, and also in here we're going to define the effective vertical stiffness of these structures. So if you calculate the very good values, you can find a good result. So I find this value as a trial and error method for this two-dimensional modeling. And in here we're going to run the analysis with 50 iterations with the maximum period as a 0.36, and then running the pushover analysis, then dynamic analysis, and then outputting the data to the text file, and also trying to read the outputted data. And in here we're going to calculate the damage index properties for these 50 iterations. And you see that, guys, in here all the process is the same. I told you that the kind of analysis which I told you about 10 minutes ago. And let's see the other outputted run analysis such as sensitivity analysis. So in sensitivity analysis, we have the same process, same functions, and also running the same process, but we're going to change the sections width and thickness, and then seeing the period and also damage index properties. And let's see, all the process is the same as response spectrum analysis. You see that, guys, in here we're going to plot it the Warren railroad truss, and in here we're going to run it. So in here with the 60 iterations we're going to change the random box width and thickness from minimum to maximum, and then actually it is not the random, it is the we're going to use the linear relations. So we're going to run the pushover and define the box 1 width and thickness, and then running the pushover and dynamic analysis, and then outputting the data for calculating the ductility damage index. And then you see that, guys, after about 12 hours we get the solutions with this analysis, and then outputting the data. And in here we're going to output it all data and run it and plot it, and showing the ductility damage index and even strain damage index of each element. You see that, guys, in here after 6 iterations, the period of the structures and velocity, acceleration, displacements, and base shears going to be shown in here, and also relations between this displacement velocity and acceleration with natural frequency going to be shown in here, and also 3D plotting of each element properties which I told you before. It's going to be shown in here. And also you see that, guys, in here in some point of this suddenly structure is going to be collapsed because structure is going to be softening. And let's see the other properties which I didn't told you before. Yes, all the parameters and plotting here which you seen, I told you about these properties. Yeah. Yeah, all the properties I told you. Yes, guys. So in the third Opensees file, I'm gonna show you the movable displacement behavior. In this file, we just run the pushover analysis of each node and then trying to see the result. So all the process is the same as which I told you, but in here with 31 iterations we're going to apply the incremental displacement during the length of this total length of this railroad truss. So you see that, guys, in here I defined the if function to apply the each node's incremental displacement, and then running the pushover analysis in what definition of nodes, elements, and section properties. And also you see in here in the definition of node 1 and node 2 we're going to apply the incremental displacement as a specified demanded node, and seeing the result. And in here we're going to output it the result. You see that, guys, in here I told you about this shape of these structures with the movable displacement. And it is very efficient, guys, for running this kind of bridge loading and finding the critical conditions for which is going to be happen in uncertainty conditions of this life safety of this kind of bridge. So you must be very careful to run this kind of analysis for your modeling of these trusses or even bridge elements properties. All the process is the same. Yeah, so you see that, guys, I run three kind of analysis. So response spectrum, sensitivity analysis, and also movable displacement for this railroad Warren truss. And also I added the optimization problem which I added in GitHub for you to run it and find the optimum section with the defined demand damage index, and finding the optimum solutions for finding the optimum section. So this video which I prepared is just for educational purpose. Please have a comment and tell me know about kind of modeling. God bless you, guys. Bye.